Welcome to the Walton Pi. Today we're going to be talking about arc length, both in regular coordinates, parametric coordinates, and polar coordinates. So the general idea is that if we have a function f of x and we want to know the length of the curve between 2 points, we can determine the formula for the arc length by looking at a series involving the Pythagorean theorem. So for example, if we are trying to figure out the length of this curve, we can approximate it by looking at these triangles. And so if we take the limit as the number of triangles goes to infinity, we are then going to be able to evaluate the actual curve. And if we were to look at this limit, there's a way to rewrite it so that it is then an integral. So if we are looking at the limit as n goes to infinity from k equals 1 to n of delta x squared plus delta y squared, because delta x is the change in x, so that's the bottom leg of a triangle, and then the delta y squared, delta y is the vertical change, that's going to be the second leg of the right triangle. And so this is just saying the length of the hypotenuse is the square root of a squared plus b squared. So this is just using the Pythagorean theorem. What we can then do is if we pull out a delta x squared from everything inside the square root, we get a 1 plus delta y squared over delta x squared, which is, in other words, delta y over delta x squared. So we can then pull the delta x squared out from the square root, so that becomes the limit as n goes to infinity of the sum from k equals 1 to n of the square root of 1 plus delta y over delta x squared and the square root times delta x, which is just the definition of the integral from a to b of 1 plus f prime of x squared dx. And so this is the formula for arc length. So let's use that formula to calculate the length of the curve of f of x equals 3x squared plus 5 from x equals 0 to x equals 2. So arc length is the integral from a to b, so 0 to 2, of the square root of 1 plus f prime of x squared dx. So f prime of x, that's going to be 6x. So it's the integral from 0 to 2 of the square root of 1 plus 6x squared dx. Now this, in order to integrate it, we are going to have to do a trig substitution. So we are going to substitute tangent of theta for 6x. So in other words, x is tangent of theta over 6. So then dx is 1/6 secant squared theta d theta. So plugging all of those in, we get this, the integral from x equals 0 to x equals 2, because I did not want to convert that into polar coordinates. And so then we are able to then get the square root of 1 plus tangent squared theta times 1/6 secant squared theta d theta, which is 1/6 the integral of secant cubed theta, which, if we need to integrate it, feel free to check out my video on how to integrate secant cubed. But the integral of secant cubed is this monstrosity. So we evaluate that from 0 to 2, and so this becomes 1/12 secant of arctangent of 6x times 6x plus the natural log of secant of arctangent of 6x plus 6x, evaluated from 0 to 2. Absolute mess, but when we go through and plug in the different numbers, we can rewrite secant of arctangent of 6x, that's the square root of 1 plus 6x squared. And so this ends up being the square root of 145 plus the natural log of the square root of 145 plus 12 over 12. And so that is the arc length of that curve. These integrals are rarely nice ones to be able to calculate. You usually have to do some sort of these trig substitutions or come up with other clever substitutions because they are rarely nice integrals to compute. So let's do a similar chain of summations to what we were doing with our standard arc length formula to find the arc length of a curve if we are given it in parametric representation. So we're going to start off at the same starting point. So we have the limit as n goes to infinity of the sum from k equals 1 to n of the square root of delta x squared plus delta y squared. This time, however, instead of pulling out a delta x squared from everything, we're going to pull out a delta t squared. Since x and y are both going to be functions of some other variable, let's call it t. So by doing so, we are able to rewrite it, and it turns into the integral from starting to end, so from alpha to beta, of the square root of dx dt squared plus dy dt squared times dt. And so it's basically the same process and same logic that we were doing to figure out what the formula was for arc length of standard coordinates. It's just using the same thing and recognizing that because they're parametric, we can pull out a delta t. So if we were to calculate the length of the curve formed by the parametric equations, x of t is t squared minus 5, and y of t is 2t cubed plus 7, where t goes from negative 1 to 3, we can calculate the length of this. So it's going to be the integral from alpha to beta of the square root of dx dt squared plus dy dt squared dt. We can find dx dt, that's 2t, and dy dt, that's 6t squared. And so it's the integral from negative 1 to 3 of the square root of 2t squared plus 6t squared squared. So the integral from negative 1 to 3 of 4t squared plus 36t to the fourth. We can pull out a 2t from inside the square root. So we get the integral from negative 1 to 3 of 2t times the square root of 1 plus 9t squared. Here we're going to be doing a u substitution. So if we say that u is 1 plus 9t squared, then du is 18t dt. So the 2t dt that we have outside the square root, that becomes du over 9. So this becomes the integral from t equals negative 1 to t equals 3 of the square root of u over 9 du, which fortunately is not too bad to calculate. So that's 2u to the 3 halves over 27, evaluated from t equals negative 1 to 3. Replacing u with 1 plus 9t squared is then going to be able to give us the answer of 16/3. So the arc length of that curve was 16/3. Now, there's one other coordinate system that there's an arc length formula for that I'm going to cover in this video, and that is polar coordinates. So when we are given the curve in polar form, there's also going to be a formula for the arc length of that curve. We can find the arc length for the curves by writing them as parametric equations in terms of theta. So x is going to be r of theta times cosine theta, because the radius might change. So that means that r is going to have to be some function of theta, and then y is going to be r of theta times sine of theta. And so by using our parametric formula, we get this integral from a to b of dx d theta squared plus dy d theta squared d theta. Now, using a little substitution by knowing what dx and dy are in terms of theta, we find that this is going to become dr d theta cosine theta minus r sine theta all squared, because x was r cosine theta. Taking the derivative of that using the product rule gives us dr d theta times cosine theta minus r times sine of theta. And so if we were to expand out all of that, so FOIL out the dr d theta cosine theta minus r sine theta, and that squared, and then expand out the other one, there will be some terms canceling, and that's signified by the 0 dr d theta. All of those terms end up canceling. And so what we are left with is dr d theta squared times cosine squared theta plus sine squared theta plus r squared sine squared plus r squared cosine squared, all under the square root, and that can simplify down to just dr d theta squared plus r squared inside the square root times d theta. And so this is going to be our equation that we are going to use whenever we need to calculate the arc length in polar coordinates. So, what is the length of the curve formed by the polar curve r of theta equals 3 sine theta between the bounds of 0 and pi halves? Well, the arc length is the integral from a to b of the square root of dr d theta squared plus r squared times d theta. So that's the integral from 0 to pi halves of the square root of 3 cosine theta squared plus 9 sine squared theta d theta. So that's the integral from 0 to pi halves of 9 sine squared plus 9 cosine squared. Well, that's just going to be the integral from 0 to pi halves of the square root of 9. So the integral from 0 to pi halves of 3, or in other words, just 3 pi halves. And so that's going to be the arc length of that curve. I hope this video was helpful in understanding arc length and being able to recognize how you can derive all of them using the same series if you ever need to or just can't remember the formula. If it was helpful, please like and subscribe so that I can continue to make these videos. Have a great rest of your day and good luck with the rest of your math.